Hello and welcome to part 5 of our video series on feature engineering, dimensionality reduction, feature selection, and feature extraction. In part 4 of this video series, basically in the previous part, we talked about the introduction to PCA, which is a feature extraction technique and actually very famous feature extraction technique. And we talked about the motivation behind principal component analysis, and we also talked about the maximum variance preservance property and the minimum reconstruction error property. Also, it preserves the Euclidean distances, pairwise Euclidean distances of the original data as well. We also talked about kernel PCA, which is a nonlinear form of PCA. And we talked about a lot of other neighborhood dimensionality reduction techniques, including MDS, isomap, LLE, Laplacian eigenmaps, maximum variance unfolding, and we saw that all these are basically special types of kernel PCA, or they can be linked to kernel PCA through different kinds of kernels. In this particular video, we are going to talk about the mathematical derivation and the underlying complete maximum variance perseverance property of principal component analysis. So the goal of this particular video is to go through the mathematical derivation of PCA, and we will be using that particular derivation for our next part as well to implement PCA from scratch using NumPy in Python. So let's start the derivation of PCA with the property that it basically preserves the maximum variance of the data. So let's see. For that, let's say we have X, an original data matrix, where X is a matrix with n data points, and D is the dimension of the data points. So for example, X can be thought of as something, all these real numbers, and then this is the first sample point. The second sample point is this. So each sample point consists of D numbers, and we have basically n of those. So this is the original data matrix, let's say. That's our data matrix, yeah? So this is X, let's say. And the dimension of this data matrix is D. Basically, there are D rows or D features of the data, and we have total n data points. Okay, so that's our matrix. Assume now we want, assume that Y is basically, again, the data matrix with n points, but only with k features rather than D. So Y consists of, let me use a different color for Y. Y consists of a lot of data point, a lot of features, k of them, but we again have n data points consisting of k features. So this matrix Y basically has k rows, again n data points. And W is a matrix which is D by K. So this is basically a matrix with D rows and K columns. So that is this kind of matrix, some matrix. And basically what we really want is further think about this first data point. This first data point, it mapped to this data point. So the original data point has k features, then it original data point has D features, and then it mapped to a data point with k features, and this W is a matrix that actually does that mapping. Similarly, the second data point maps to second data point in Y, and so on. So this relationship can be seen using this. If xi is the ith column, that's the, let's say, ith column. If xi is the ith column, and so ith column will be D by 1, and W is D by K matrix. So the transpose, this T represents the transpose of the matrix. So this transpose is basically makes this as K by D. So the result Yi then will be K by 1 vector, and this is the ith vector here in Y. So that's the relationship. That's the relationship that is there. So Yi is equal to W transpose Xi. And now you can think the columns of W, the columns of W as x's of the subspace. The columns of W, they are x's of the subspace. Not only the x's, they are basically orthogonal x's or orthonormal x's. Orthonormal. A vector is called, two vectors are called orthonormal. So let's say we have a vector A and a vector B. They're called orthogonal if their dot product is 0. If A is a column vector, B is a column vector, their dot product is 0, we will call them as orthogonal. If both A and B are column vectors, the dot product can also be written in this way: A transpose B as a matrix multiplication, which is equal to B transpose A as a matrix multiplication, as long as both are column vectors. And if that is 0, then we will say both are orthogonal. Further, if their magnitude, if A magnitude is 1 and the magnitude of vector B is also 1, then we will call them as normalized vectors. So if two vectors are orthogonal as well as normalized, we will call them orthonormal. So the columns of this W, each column, there are k columns, there are k axes. The columns of this W, they are orthonormal vectors or orthonormal axes of the subspace which is going to fit the data. We do not know that subspace. We do not know these x's. We actually have to measure those x's. We have to find these x's. Once we know the basis or the x's of the best subspace that fits the data with only k dimensions, then after having this W, we can transform our x to y, and the dimensionality basically is reduced. So that's the goal. Till now, I have not introduced that this subspace can be found using max variance preservance property. I'm just saying that this W is a matrix with k orthonormal x's or bases of a subspace that we do not know which one is that. But all we know is there is a k-dimensional subspace upon which which may best fit the data. Or if we want to fit the data using k-dimensional subspace, what are the bases of that subspace? What are the x's of that subspace? We have to find those out. And it turns out that this is the relationship. If the columns of Y, they are x's, orthonormal x's of the subspace, then the orthogonal projection can be carried out using this formula. Yeah, that's a simple formula for doing that. Now, rather than transforming one column at a time, we can transform the whole matrix once using this W. So think about this W as K by D, and this data. So this W transpose basically is K by D. This X is D by N, and this once this carried out, this Y becomes basically K by N, which is this. And the goal really is to reduce the dimensions. The goal really is that our K, which is the dimension of the subspace, that should be much smaller than D if we really want to reduce our dimension. So that's the setup. If the columns of W, they are orthonormal x's, orthonormal bases of the subspace, then we need to find out those bases. Once we have those bases, then we can transform our original data. We can reduce the dimensionality of our data using this formula. Okay, so far so good, I guess. Now we dive into the max variance property. What should be the property of the axis of this W what should be the property of the columns of this W that we want to maintain to transform X into Y? Well, the property is the axis of the W should be in a way that the transformed vectors yi is the transformed vector of the xi that has maximum variance. For simplicity, think about projecting onto one-dimensional space. So think about k is equal to 1 for now, just for simplicity. Later, I will relax that assumption. So if, let's say, we have only one dimension to keep, we are going to reduce the dimension to one dimension. Whatever the dimension, let's say original dimensions are 100, so D is, let's say, 100, and we are going to reduce the 100-dimensional space to just one-dimensional space, let's say. Then yi is simply the W transpose xi. In this case, W will be just one column vector. W will be a vector with just one column because k is equal to 1. So that's a vector, which is basically d by 1. That's a vector d by 1. So W transpose will be 1 by d. So that is d by 1. So this yi will be 1 by 1, which is simply a scalar, which is just a number, real number. And because yi is a number, in the case k is equal to 1, y transpose is also the same number. So if k is equal to 1, yi is equal to yi transpose. So what kind of W, what kind of this column that we really want to find out, what should be its property? Well, its property should be when we project all our data, the projected data or the transformed data or the data with reduced dimensionality, it has maximum variance. And how you compute variance? You pick every number and you subtract every number from its mean. I should use this, I have used this hat symbol that should not be used, and by the way, because this hat in statistics shows the estimator. That's a popular notation for estimator, but here I'm using this to represent the mean, sample mean simply. So yi is the ith data point projected. Y is the average or the mean value of all the projected data points, and the square of that over all I, that basically represents the variance of the projected data. And I really want this W to be such an axis that maximize this variance. Remember in the last video I talked about that we need a subspace that maximizes the variance because that reduces the error in projection or sometimes the reconstruction error. So basically we want Y, basically we want W that transforms X in such a way that after the reduction of dimensionality, the variance of the data is as maximum as possible because this is the variance of the data that is linked to the information that is maintained or retained from the data. This is for k is equal to 1, by the way. For k greater than 1, this particular formula, yi minus yi hat, this actually goes, so for k larger than 1, this particular formula, this yi minus the mean, this can be written as yi because now yi will be a vector rather than just a one number. It will be a vector of more than one values, minus y mean will also be a vector, and then we will be computing a squared norm, maybe a Euclidean norm of this. So this formula goes to norm squared if k is larger than 1. And that's particularly the reason that norm square, if we open the norm square, that basically becomes this. So if you have for example, if you have a vector A, its norm square basically equals to A transpose A. So the norm square of yi minus yi hat is simply this vector transpose itself. It is not needed in the case of k equals to 1 because the transpose of a scalar, because yi is a scalar, if k is equal to 1, y mean is a scalar, that is, and the scalar transpose is a scalar, so we need not write this way. But when k is larger than 1, these parentheses, they goes to they go to basically this norm symbol, and from there this carries out naturally. So next we see how to basically move from here onwards, which is basically, again, we are thinking about k is equal to 1. We will see shortly the case when k is larger than 1. If we have only one dimension to keep, how this moves to, how can we find out the w, which is a column vector, which is the basis of the subspace. Now think, because k is equal to 1, yi is the same as yi transpose, so we can use this thing or this thing, either way, whatever we like. So what we really plug in here is this formula, xi transpose w, in place of yi. So let's see what turns out. So this goes to max summation yi replaced by xi transpose w minus this y hat replaced by x mean w, x mean transpose w whole transpose into, so remember this particular thing, yi is equal to yi transpose in the case of k is equal to 1. It is not true in the case when k is larger than 1. But in the case when k is equal to 1, yi is a scalar, yi transpose is a scalar, and they are same. So now we have this yi can be written as xi transpose w minus x mean transpose w. It can also be shown that under this transformation, the mean of the original data, it maps to the mean of the projected data. So it can be shown that y mean is basically w transpose x mean, where x mean is the mean of the original data. It can be shown that this is true under this linear transformation. Now after this, we have now this particular formula, and let's move this formula, let's unravel this formula to go what turns out. Let me go to a slide with more space to derive this formula. So let me write this formula again. Let's say we have max summation I varies from 1 to n, xi transpose w minus x mean transpose w transpose, and then we have xi transpose w minus x mean transpose w. So that we really want to maximize. We really want to find out this w that maximizes this. Remember, this is yi, this is y mean, this is again yi, this is y mean, as long as k is equal to 1. Now if we apply this transpose, before applying this transpose, you can see that this can be written as, we can take this w common minus x mean, this transpose, and we can take this w common, and then we have a total transpose out. We can just pull this w on the right hand side, and we have this, and on the right, on this part, we can have this xi transpose minus x transpose, and this is the w that is basically the w is here. Yeah. So now if we apply this transpose, we get so this w out, and now we can apply this transpose. And remember, transpose of A, B whole transpose, where A and B are matrices or vectors, compatible vectors with the product, that is equal to B transpose A transpose. So using this formula, you can see you can think of this matrix as A and this matrix as B. So A, B whole transpose is just B transpose A transpose, and that gives basically, let me write that, that basically gives W transpose xi transpose minus x mean transpose, and then we have this xi transpose, sorry, this transpose is also there. Yeah, so this transpose is there. xi minus x mean transpose w. Now further, a plus b whole transpose, that is equal to a transpose plus b transpose. So if you think this as that, and same goes for minus as well. So a minus b transpose is a transpose minus b transpose. So this transpose will be applied on this separately and on this separately. And one more property, a transpose is equal to a. So using these two properties, we can get max I varies from 1 to n w transpose xi minus x mean. The transposes are applied, and then we have this xi minus x mean whole transpose, again due to this property w. Now you can see this w has no index I. This can be pulled out from the summation, so we can have max w transpose I varies from 1 to n xi minus x s, and then we have xi minus x mean transpose, and then this from this summation, again that's the summation, then we have this w again out. So this matrix, which is every vector, the mean vector is subtracted from every vector, and then the outer products, this can be rewritten as this matrix can be rewritten as xc transpose, where xc is x, but every from every column of x, the mean vector is subtracted, so x centered. So then if you multiply this x centered by x centered transpose, you actually get this matrix inside. So the actual goal that eventually comes up is the following. So you have x-centered transpose, and then you have w transpose, and you need to maximize this property. So that's what the turnout is. It turns out if you really want to maximize this particular thing, where this is sometimes called the covariance matrix from the data. It can be computed from the data. So this covariance matrix can be completely computed from the data. So we have our data available with us. If you remember this data matrix, just subtract from every column, just compute the mean of the data, which means add all the columns, divide by the total number of points. That will be one vector. Subtract that vector from every column, and you will again be having a matrix that you should call xc, x-centered, because it is mean-centered, mean is out. That matrix will again be d by n, and that is this matrix xc. If you multiply xc with xc transpose, that famous matrix is sometimes called covariance matrix. It has so many properties. It is positive semi-definite. All its eigenvalues are non-negative, and all its eigenvectors, I mean the eigenvectors can be computed as orthogonal, and it has a lot of other properties. So given this matrix that can be computed through data, we need to find out w that maximizes this criteria. Again, if you see this w transpose is 1 by d, and this particular matrix is d by n, then we have n by d, and then we have d by 1. So all this thing eventually is one number. So we need to maximize this number, and we want to find out such a w. You can see we can maximize this number to scale up this w. For example, we can just multiply. If we have some w that maximizes this criteria, we can have another w, for example w dash, which is just 10 times the original w, and it has maximized the more criteria, and so on. So if we do not restrict the scale of the w, the magnitude of the w, then we can have we cannot have a solution, unique solution, because for every w there is another w that is better than the previous one. So normally we want to maximize this with a constraint that we are only interested in the direction, not in we are only interested in the direction, not in the scale of w. What is the direction in which the variation is maximum? So normally this constraint is deployed, And maximizing this criteria using this constraint, one can simply show using Lagrange multipliers, Lagrangian dual of that the best vector W is basically the eigenvector of this covariance matrix. So the eigenvector with maximum eigenvalue. So we have this matrix, which is covariance matrix. We will compute all its eigenvectors, and the eigenvector with maximum eigenvalue, that eigenvector corresponding to the maximum eigenvalue basically maximizes this criteria. And if we, for example, move to more than 1, if k is larger than 1, then this particular stuff is no longer a number, that becomes a matrix. And maximizing, we cannot maximize a matrix. Again, we can move to this particular criteria, and we have a norm there, and if we expand the norm, then the final criteria will turn out to be trace of this. We want to maximize the trace of this this matrix. Now this will be a matrix rather than just a vector, where k is larger than 1. And it turns out that if we want to maximize the trace of this particular matrix, where this matrix is again a covariance matrix, if we really want to maximize the trace subject to this constraint that this is identity matrix, then again the best k vectors are the top eigenvectors of this covariance matrix, where the top means the eigenvectors corresponding to the maximum eigenvalue. So that's the derivation of PCA. I have, in limited time, I have skipped a lot of steps. I know there can be much more explanation for this, and I will refer you to see our full course on dimensionality reduction for detailed and bit-by-bit derivations and all the concepts related to this in much more detail. But here I have just sketched the derivation, and it turns out to be eigendecomposition of a particular matrix. In this case, it's a covariance matrix. It is important to know that all the several other methods, for example, isomap, locally linear embedding, Laplacian eigenmaps, maximum variance unfolding, and all these kind of stuff, they also turn out to be eigendecompositions. However, in maximum variance unfolding, that turns out to be a optimization program, convex optimization program, which is semi-definite embedding. But in several cases, when you will be applying dimensionality reduction, one way or the other, you have to do this eigendecomposition, because the objective at the end of the day will turn out to be this kind of function. But this matrix might be different for different kind of techniques. In plain PCA, in simple PCA, that is a sample covariance matrix, but in other methods, that matrix will be different, but the criteria will be more or less the same. So yeah, so with this derivation, in the next part of this video series, we will be implementing a principal component analysis from scratch, and actually we will be reducing the phase. We will be reducing the dimension of the human phase data set, and we will be then reconstructing the data set again back. So yeah, hope to see you in the next video with the implementation of very famous technical term called eigenphase, which is just the principal component analysis on phase data set. So hope to see you in our next part.